let's start by talking about the multicore certification landscape, and in particular, one of the first topic will be to look at for which reason are you going to multicore. And there are two groups, I would say, of good reason to move to multicore. The first one is when you do consolidation of legacy single core systems. So there are several keywords here: consolidation, legacy, and single core. First one about legacy, hardware obsolescence is a typical reason why you may want to move to multicore, because it's simply difficult to find a single core processor more and more. The second reason is because one of the value of the multicore, it's you have multiple cores, so you can do consolidation and reduce space, weight, power, and cabling to put several legacy systems into one from this point of view. And a side effect, so this was looking from the system point of view, but if you look for the system, for the equipment itself, you can reduce the bill of material, which can reduce your cost. The other reason is to continue something that started with even single core processor, it's to do integrated modular of Unix. So this is a particular way of looking at consolidation. The IMA approach allows you to update, for example, one application without having to revalidate the whole system. So that's another step on the consolidation. But these are the typical use cases that you may want to go to multicore. If you do that, there are side effects, like in particular, when you move legacy system, you have legacy OS that comes with your application. And maybe your application does not translate to a new OS that works on the multicore, I would say, and you have to do some porting. But with the multicore, maybe you can find a way to keep that legacy OS in there. So that's something to keep in mind. When you consolidate as well from multiple legacy or federated system, they could be a different kind. It was maybe not the same OS used on all these systems, so it could be heterogeneous. So that's another thing to keep in mind. And in the end, also linked to that consolidation aspect, you may have mixed criticality to do that will impose to do some partitioning activities to guarantee that mixed criticality. But you may want to use partitioning as well for other reasons, like minimizing the cost of updating the system. So that's one kind of reason why you want to go to multicore. The other one is more related to innovation, which means that you want to have more computing power to run new, I would say, kind of application. And for that, even the single core was too short from that point of view. If you want to do image processing, so to automate some process based on video that you will analyze on the live, to start using artificial intelligence, machine learning, and also predictable maintenance. So these are new activities for which you will need certainly more computing power. But also simply because you have a multicore, you have more computing power, you may just want to provision for growth, meaning to be able to add new application later on. So that's the scope. That's the landscape you need to keep in mind, because your objective can drive some of the choices you will make it later on. So to finish on the landscape part, the multicore certification comes with some guidance and objective that have been set up by certification authorities. Study on this topic started even before 2009, but you start to see the first guidance back in 2014 with the first version of the CAS32 that was replaced in 2016 by CAS acceptance needs of 20-193 in 2022, which was a joint work with the FAA. The FAA was just a little bit slow to publish it, and it has been released this month, so January 2024. So now this is the guidance that needs to be applied. And Karl will talk a little bit more about it, in particular regarding the action that has been defined. So as part of this action, usually you have the planning phase. That's how you're going to make the link with DO-178C and DO-254 for the hardware and software aspect. And then the other activities, the objective of them will be for you to understand your multicore, meaning be sure that you understand how to configure it, what are the aspect of it that you need to take into account. Then identify, assess the interferences that could impact your application, mitigate them, so find a solution to work around these interferences and verify them. And Karl will go into more detail on this topic right now in this section. Up to you, Karl.
Thank you very much, Olivier, for introducing the certification aspects of multicore interference and the landscape in general. I'm going to briefly now introduce what multicore interference is, and just for the purpose of introducing some context for talking about mitigations later. So if you want a deeper dive into multicore interference, because this will be a whistle-stop tour, I refer you back to our previous webinar, which I'm sure marketing would be happy to provide you with a link to if you ask them, which was a deep dive into multicore interference. So as Olivier introduced previously, we are specifically talking about the CAS32A objectives, or the AMC, or now the AAC 2193 objectives. And in particular, we're talking about interference channels. So per definition, an interference channel is a platform property which can cause interference between applications and tasks, and software applications and tasks specifically. And the objective of interest here is MCP resource usage 3. And specifically, what this objective demands is that interference channels are identified, characterized, and that a chosen means of interference is also verified. So from here on, to sort of introduce interference channel identification activities, characterization activities, I'll be aligning with terminology from our MAC 178 certification product. I'm sure there are different names as well, but it's just the simplest way of guiding you through it. So let's first talk about interference channels. So we internally, and for simplicity's sake, like to differentiate interference channels by categorizing them in 3 categories. These are direct, indirect, and unknown. So the first we consider is generally the most accessible, which is direct interference channels. So generally these come in the form of direct competition for resources or bandwidth, which comes from different tasks on different cores, or applications on different cores. So these bandwidth contentions can, as you can see, include things like cache evictions, so competition for a shared cache, or other resources, specifically memory accesses, are particularly prone to this, and complex memory hierarchies, which are present in multi-core systems, often are susceptible. The next category are indirect interference channels, which are generally based on unpredictability of hardware execution. So this can impact execution time. For example, if you have a ring buffer in which you have multiple devices attached, and a particular route is generally the preferred route, but different devices channeling traffic may disturb that route, and therefore going all the way around the other way of the ring buffer may suddenly be preferable. So in a multi-core system, suddenly, rather than having the preferred route every time, you may unpredictably be forced to take a different route, increasing execution time. And again, something that will be mentioned a lot is decreasing the predictability of your execution time. Another thing would be cache coherency. So again, you'll hear mentioned a lot, caches specifically, and other memory hierarchy elements, which often have a lot of interference channels associated with them, come along with cache coherency protocols to ensure that shared data is coherently handled. For example, on the NXPT series, this is handled with Snoop requests. Generally speaking, that's true for a lot of other platforms too, but specifically, they are handled on the NXPT series preferentially. And this means that a Snoop request must always be serviced before a request from the local core to a cache. Now, that makes a lot of sense for cache coherency in general and for memory coherency and data. However, what it can mean is that a flurry of Snoop requests may actually block cache usage entirely, i.e., a core is handling, or a cache is handling those requests over direct core activities. And the third category, which hopefully is the scary category, it should be, is the ones that appear when we don't know why originally. So this is something we haven't identified as direct or indirect, but something that comes up when testing or characterizing an interference channel, when behavior pops up, when timing behavior pops up that we can't explain with what's been identified previously. I won't go into examples. If you want some more in-depth examples for that, okay, I'll give you one quick one, which is, for example, we have come across a platform where the DVFS, so dynamic voltage and frequency scaling, was turned off, which is a good thing generally for timing predictability. And so that is something you want to have turned off. However, it turned out that by hammering the FPU of one of the CPUs, it was possible to cause it to thermal throttle. Now, thermal throttling meant that the DVFS actually switched itself back on, leading to the frequency being reduced, hence the thermal throttling action. Now, that sort of unknown interference channel can lead to problems down the line, and this has always been something that has come up, and that we've not come across a single platform that hasn't had some of these. So now that we've, let's say, identified what our interference channels are, we've gone through the documentation according to our processes, we've identified a number of these interference channels, we need to move on to characterizing them. Again, this is a whistle-stop tour. This is by no means an exhaustive discussion on how to do it, but we need to introduce characterization so we can move on to mitigations. So for characterizing interference, we need to start thinking about how we can stress an interference channel. So the first thing we need to do is design a piece of code which is sensitive to the interference that we will then try and generate, and that is predictable enough and that we have enough understanding of to run in isolation and understand what the hardware operation itself does. So for example, if we are looking at a simple DDR interference channel, we might be trying to measure how many normal reads we make to the DDR, and we want a piece of code that is very predictable and executes a certain number of reads very predictably. So internally, our product is the RapidDaemon, which is a piece of code that can do this. They are complex because they need to be qualified, and they come with a qualification kit accordingly. And we run that on our core in isolation to get some measurements. Now what we need to do to characterize the interference channel is we need to run some aggressive RapidDaemons, so they effectively make as much noise as possible, and they also need to maximize this interference, so they need to be shown to also generate the maximum amount of interference they can on the other cores. And naively, you might say, well, the best way to do that is to place as many interference generators on the other cores as possible, because the more interference you generate, the more noise, the more impact you'll see. Now, this is often true, but we have also seen cases where interference is not simply additive, and at the very least, at least the next graph should show that it's at the very least not linear, so it's not quite that simple. So here we have an execution time histogram where the green bar is the code running in isolation, and this is timing on the x-axis and frequency on the y-axis. The green bar is the sensitive RapidDaemon running in isolation. The red is with one core, also running an aggressive RapidDaemon, the blue with two, and the pink with three. And as you can see, it is not a linear increase in execution time, but it is a factor of 2 increase in execution time when you have 3 RapidDaemons running on the other cores versus none. So you should see here that hopefully that the interference is not a simple linear process, and that execution time is a main concern. So naturally, also that's what we're here talked about, is how do we mitigate this? So what is interference mitigation? So as you see here, there's another example of some interference, and we've seen that it could increase the execution time. Here we can also see that the spread of execution times is drastically increased, again with 1, 2, and 3 RapidDaemons. This is a different interference channel on a different platform. So the aim of mitigation then would be to reduce the worst case execution time, as well as reduce the span of potential execution times. So we want to make it more predictable and ideally less bad. So what we need to realize as well is that not every interference channel can be mitigated, and even if they cannot always be fully mitigated. With that in mind, we're going to go into some examples, specifically some hardware and some software mitigation examples, and talk about what specifically you might be able to do and how you can approach mitigating interference channels. So some hardware mitigations would be quite simply, or the simplest one would be to disable a hardware device completely. So if you have identified some interference channels associated with a hardware device and you decide it's not a device that's necessary to use, it might be simpler to just disable it completely. If it's not being used in an application, not having to consider it would be easiest. Now, it still has to be verified that it is disabled, how it is disabled, and that it is completely disabled and cannot be switched back on. These are parts of the objectives, but it is an approach you can take. Otherwise, you might want to disable a hardware feature. So you say, well, I have a feature, for example, L2 cache snoops, not snoops, sorry, stashing, that, for example, where a device can place data into an L2 cache. That is associated, has some interference channels associated with it. Well, I want to disable that feature in my configuration settings. That would be a way to mitigate that interference. You'd still have to show that this has happened and that your configuration setting is mitigating the interference as you expect. We'll go on to verification slightly later. Otherwise, you can manage the access management. What we mean here is that a device, for example, may have an MMU configured with it, or an IOMMU, to only allow a single task to access the resource during any given scheduling window. Now, for really complex devices, you can maybe even circumvent multiple interference channels at once by selecting the hardware appropriately. So there may be an on-chip complex system, for example, PCIe, an on-chip peripheral that you might be using, but instead you might have a very much simpler PCIe version to an off-chip version, which might have fewer interference channels associated with it, which could be substituted. That might feel a little counterintuitive to disable something that's already available on the chip and add something additional, but it might be that the usage of that device is limited to a scope where the off-chip version is able to handle what is required of it, but is simpler and more analyzable and less susceptible to interference, or has fewer interference channels. So these would be sort of hardware mitigations that we might use as approaches. There are also some software mitigations we might look into, and this is by no means an exhaustive list. This is just some to give you ideas. And hopefully it's also clear that none of these are without a trade-off. There is always a trade-off, and we'll go into that in a second as to what exactly you gain and what you lose. And especially now we come into the software ones, you see that most do not fully or cannot fully mitigate interference channel. So for example, you might want to time slice a resource. So effectively in software, only allow one task to use a particular shared resource during any scheduling period. And you might have software-mediated access to a device. For example, you might have a storage server task which mediates the access and serializes the accesses from multiple cores to a particular device. Now, this would allow you, as the user, to no longer be dependent on the hardware implementation for the serialization, which may be badly documented, if it is at all, and also may be hard to manage or hard to mitigate any interference that arises from it. Another approach would be potentially to allocate an IDAL window per scheduling window. So if you previously had a scheduling window with mixed criticality applications running within it on their various cores, as you can see here, you may be able to separate that into multiple scheduling windows on multiple cores, which means that you no longer have to take in considerations that will be required for DAL A when looking at your DAL E application, which also often DAL E application might be doing some more complex things with video processing, etc., which might have resource implications. So being able to move that into a scheduling window and move it out of consideration when you're considering your DAL A or DAL B applications might make, at the very least, the analysis easier. Another thing that you could look at is, let's say you have a task that has some inputs and processing and some output. So you have a task with multiple elements and multiple resource accesses within it. You may be able to partition those tasks and place them into a different scheduling plan. For example, as you can see here, you've taken this task and broken it into its input, output, and processing elements and allocated those so that you no longer have the same resource usage at the same time, or so that you have the ability to have a bit more control over your schedule. Now, this comes with a potential other mitigation benefit, which may be that you can segregate the data exchange that you have between period boundaries. Now, doing that means that your usage access profile, for example, for a resource, might be simpler, and the scheduling can now take control of resource usage and access patterns. So this way, data is always available when required, and it can take some difficulty, especially in the analysis, away from mitigation and interference in general, identification and characterization. So now that we've seen some examples, hopefully it's clear that there are some trade-offs, and generally, and this is as a consequence of multicore processes in general, and like Olivier introduced before, why they came about in the first place. One of those reasons was for their increased performance. Now, often this increased performance, when the chip or in the part was designed, came for the purpose of increasing the average performance. And average case performance doesn't help us much when we're considering worst case performance in general. So a lot of the, for example, features and hardware features that come along with having multiple cores and having deeper levels, deeper memory hierarchies, more complex chips in general, often those abilities or those functionalities will come along with a lot of interference channels. So reducing their functionality or disabling them always will come with a performance hit. But as you can see, sometimes that may be worth it to mitigate the channels in question. As a concrete example, having a level 2 cache obviously can be very beneficial for performance for accesses to memory for given applications or for certain applications. Having a shared cache can be problematic if you have evictions or pollution from other cores. That may be problematic for a given cache. And if you have a safety critical piece of software there, high criticality piece of software there, that is suddenly getting its cache polluted or its data evicted, you might have problems with performance suddenly. Again, this all comes down to predictability and performance in general. So being able to enable some cache partitioning, and Olivier is going to talk a bit more about actual implementation of mitigations, being able to implement partitioning and such may increase the predictability. So often that is the trade-off. You may lose performance for an increase in predictability. So what we need to consider here then is what else do we need, what other considerations are there that we may need to sacrifice performance for, and what other things are associated with identifying interference channels with their mitigations and characterizing them that come along with sacrificing performance or implementing a mitigation. And those two things are its analyzability and its complexity. So often disabling complex features while you use the performance obviously makes the device easier to analyze. And that's not just because interference channels might get removed entirely, but also because understanding sometimes how to stress an interference channel becomes easier when there is less in the way or fewer dynamic features that are interfering with it. So to give you an example, to be able to show that your Rapidemon is sensitive or aggressive to a given interference channel can be very complex when that is a deeply embedded device or a part of the memory hierarchy where you have to avoid other parts to get there. So for example, the data that we showed before was coming from interference channel that's associated with DDR access serialization. So to be able to show that you are exercising that or being aggressive towards that, you need to avoid L1, L2, you need to potentially avoid L3 if it's enabled in that in that board to be able to access DDR in the first place. At the same time, you also need to show that you are not stressing other interference channels, but that you are actually targeting the interference channel that you say that you are targeting. So when the system is particularly complex, to be able to analyze that may become incredibly difficult. So disabling those dynamic features or complex things while losing performance may improve your ability, or maybe enable you in the first place to be able to exercise interference channels. So I think that comes along with complexity. So we've talked about a few mitigations that impose constraints on the RTOS or the hypervisor schedule or scheduling in general. At the very least, should be considered when when there are software architecture considerations. And there may be an argument that some of them increase the complexity of a system while increasing their predictability. For example, if you impose a certain mitigation on your architecture or on your schedule, which makes the actual building of the software, the development of the software particularly complex because of a lot of considerations for interrupts, etc., or for various operations that are no longer usable, you may not be able to hit your performance requirements, etc., or it might make it incredibly complex to develop the piece of software. So the complexity can be hit or miss. Sometimes implementing an mitigation can have unforeseen complexities down the road. So now we've had a look at some of the potential mitigations that you could apply and some of the considerations you should have as to whether you do and how you apply them. Let's have a look at how you actually detect or verify that your mitigations are in place and that they are doing what you expect them to do. So if I can bring it back to the interference channel characterization activity that I mentioned previously, we there have a piece of software which is particularly sensitive to a given interference channel, which is our RapidDaemon, and we know its execution time and its execution time profile for in isolation for a given activity. Now, instead of just placing as much interference as possible or having the scenarios, the interference scenarios that we have in place to see, for example, the simple ones being a single aggressive RapidDaemon, 2 RapidDaemons, 3 RapidDaemons, however many cores you might have available, to maximize the interference, we actually put the mitigation in place before we do that. Ideally, you can reuse your interference scenarios that you would have done otherwise without the mitigation in place. Now, with the mitigation in place and generating, maximizing interference, you can then see what the actual impact of the interference now is, i.e., are your mitigations successful? How successful are they? To what are their limitations? Is now the amount of interference that you see, at least the execution time penalty that you see now, at least predictable? Is it predictable and small enough that can be built into a different engineering margin, for example? So these are all considerations that can come up now. And if you've shown that your mitigation is in place and that it is successful, i.e., if you've disabled something, you've shown that disabling the device means that this interference channel is no longer exercised. That means that you may be able to remove it from scope when it comes to later objectives, i.e. MCP software 1 and 2, which would involve again a lot more software characterization processes. So being able to remove things from scope as early as possible through mitigation, for example, would be incredibly beneficial. Some considerations you have to have here are that in MCP resource usage 3, as you can see, one of the things that is mentioned as the interference channel, but in resource usage 4 is that you also have to determine the resource usage of the applications. So to be able to identify that you're characterizing the interference channel correctly, to be able to monitor the resource usage of your software or of interference channel, you'll have to have particular devices or considerations in place. Those would be, for example, that you need to have hardware event monitors or performance counters available that can check for the things you think you're doing. It's very difficult to show that your RapidDaemon does indeed exercise the interference channel that you think it does if you can't show through resource usage that it is. For example, if I've created a RapidDaemon for DDR, to be able to verify that it is in fact exercising the DDR interference channels that I believe it is, I might need to know, for example, DDR accesses, etc., etc. If I only have performance counters for example, cycles or program instructions in place, that might become very difficult indeed. And again, the complexity of analysis there goes up. So some of these considerations should be taken into account when trying to verify your mitigations, i.e. trying to characterize your interference channels in the first place. So for some implementation ideas on this, I'm going to pass you back over to Olivier now, who will go into that.
Thank you very much, Karl. And thank you very much for describing the different kind of mitigation that could be put in place and the trade-off that comes with it. So also, as pointed out by Karl, at some point in time when you start to make your assessment about interferences, you may want to reconsider the hardware you have selected, just to make it more simple. So I would say at this point, more than just the power consumption, the computing power, and heat dissipation that you traditionally use to select an hardware, how you are going to assess and mitigate multicore could be a new criteria to take into account. But when you have an idea of the mitigation you want to implement, the question is, how do you implement that? And for that, typically, you have different kind of operating system you want to use, and that can become another criteria to select, because each of them will have pros and cons on either what kind of mitigation you can apply, but also coming back to the use case we talked at the beginning with the landscape, not all of them will implement all the use cases. So the kind of OS is also a criteria you have to take into account. So here I've put the 4 typical family of operating system that you can find on the market. And let's go through all of them to see how you can implement the mitigations. So the first one is the unsupervised AMP. Pretty much, in particular, when you want to do consolidation from multiple systems, you just pick up all the OSs and you put one on each core. It looks almost like the single core approach that you are consolidated. So you can see that from a use case point of view, pretty much all the use cases you had from your multi-core system can be usually applied here. And with this use case now, if you look at the mitigation, pretty much the OS, I would say, can only control its own code. Usually it doesn't have the privilege to go to the other one, and which means that the kind of mitigation you can apply are the hardware one that Karl described. And pretty much what you can do is resource segregation, because here again, the OS will not have access to more than this. And in particular, when you do that, the memory controller and the cache can remain an issue. So this goes back to the hardware selection. For example, if you have a hardware with multiple memory controllers, because it has clusters of cores that you can organize to dedicate a memory controller, or because you, for example, you don't share cache, because sometimes the L3 cache that could be shared could be disabled. So in that case, for such solution, that may be more suitable and easier to also make the assessment and implementation of mitigation. As I mentioned before, the OS doesn't have full control on the hardware, it more sees its own core, which means that applying the hardware mitigation to deactivate or make no sharing is something you will have to implement in the bootloader or in the safety island, because now a lot of multi-core processor has a microcontroller on the side that can be used to execute higher execution level writes to do such configuration. So that would be a baseline that could sound simple, but it restricts the mitigation that you can implement. One point here is if something goes wrong, like for example, one of the OS try to access a resource that it doesn't have access to, that will trigger an error. What you do there, so here you will have a very limited number of reactions that you can apply, except if you have the safety island I was talking before. So here's something you can do. It's to add a supervisor. So just to make the difference, because you would see that, oh, that looks an hypervisor. I will talk next about the hypervisor. Let's consider supervisor, which is a subset of the hypervisor that is just there to just react at a higher level of execution in order to manage an error or do some control or monitoring or things like that, but does not take any active action on the execution. That would be the difference with the hypervisor. So here you have highlighted in blue pretty much the differences compared to the unsupervised AMP. That because the supervisor will have to run at a higher execution level, typically the hypervisor execution level, it can perform some configuration of the IOMMU, as pointed out by Karl, from that point of view to really segregate resources. And this is where also you can apply error management and resource usage relation or monitoring in order to be able to react at a higher level of execution. If we go to the next one, which is the hypervisor and more the virtualization approach, here you enable more capabilities in terms of mitigation, and also you have access to more hardware resources to monitor what's going on. So compared to the previous unsupervised and supervised AMP solution, where you can mainly only apply the hardware mitigation, here the hypervisor brings the possibility to apply software mitigation. And we will go in further detail later on how you do that. And you have a wider range of mitigation that you can apply with such solution. And also the hypervisor, like the supervisor before, can configure the IOMMU, so or the firewalls, depending on the hardware you are using, to segregate the resources or configure some monitoring capabilities that can come in the hardware. Like the supervised AMP before, error management and resource usage relation can also be monitored. But here you can have deeper monitoring. Like, for example, the supervisor can really monitor the execution of the OS and verify that one can make use of more resources than it's required, and also consume more time, for example, that was assessed, which is one of the key objectives of the MC 20-193, that you need to make sure that you don't consume more, in particular when you want to implement partitioning, which is one of the definition of these objectives. And the hypervisor can apply a frame scheduler, so all the time slicing that was presented by Karl can be implemented at hypervisor level to serialize access to some key resources or prevent low DAL function to run when the DAL A1 runs, so it simplifies your assessment and also the mitigation. But there are some trade-off, as Karl mentioned, that you will not have the whole multi-core computing power available in the end. But here you can see that starting to bring the hypervisor, you can bring software mitigation in there. The other one that also can bring software mitigation is the SMP OS. So in this use case, the OS control all the cores. So usually the difference with the hypervisor is the hypervisor runs at a higher level of, I would say, execution, the hypervisor, while the SMP more runs in supervisor and control user space application. But still, the SMP OS can also apply pretty much the same, I would say, software mitigation. One of the differences, who is doing what, and we will go in the next slide on the detail on pushing the responsibility of doing the multi-core analysis, I would say, and proof, and also who is in charge of the implementation of the mitigation can depend also on the OS. So in summary, I would say that the SMP OS and the hypervisor-based solution can both implement hardware and software. The differences are on the responsibility we give to some people of the team. If you have a single team, doesn't make a big difference. But if you have multiple companies or multiple teams within a company working on the same equipment in the end, the choice of the OS can really have an influence on how easy it's going to be to organize the work. The other point with the SMP OS is if you come back to the use case we talked before in the landscape, when you consolidate multiple different applications that were using different legacy OS, something like that, it may not be that easy to port all of them on the SMP OS. You may have some portabilities activity to be performed in order to be able to host on the SMP OS, while with the hypervisor, the multiple OS aspect is easier. So see, you can see already a criteria to select between both. But from a software mitigation, you can pretty much implement everything with the SMP like in the hypervisor. Now, if we start to look at the detail, and maybe before going on the detail, you could say that, oh, you just talk about the SMP OS, but maybe we can use several SMP OS in AMP. You start to complexify your system, and that could be tricky to really organize how you make your Multicore assessment. So here, I try to start at a simple level from the kind of OS, but you can imagine further, but maybe it's a little bit early because Multicore certification is new for everyone, including the auditors. So keeping simple is usually, it's already complex, so try to keep it simple. So here's an example of a resource for which you have identified in your assessment that you can share a device between two applications on two cores, so here core 1, core 2, and the interference is acceptable. So here, there will be interferences, in particular if you don't segregate in time the execution, but you consider it's acceptable. So here what you can do is to push it to the application to really manage this aspect, but you have to be careful that you will have concurrent access here to the real-time clock of the two applications. So you need to be sure that the hardware will support this. And this is where you need to go back to the hardware documentation and usually have to do some testing. So the assessment that Karl was talking about to verify on exactly what is the impact on this. Sometimes you can do that, for example, in read-only mode, but you may want to prevent the writing to do that. So this is where the hardware configuration can help on only allowing read-only mode in these. And if you need to do some writing, maybe you need to apply the second approach, which is to put something in the middle in the hypervisor or SMP OS in order to physically control the hardware and only allow some function either to access directly the hardware, so which is not shown on the picture, but that's a compromise between the previous slide and this one, or have all feature go through the hypervisor or SMP OS to control that the request coming from each core is going to go well. And for that, this device that runs in the hypervisor or SMP OS can run at a particular moment in time. And you can even specify on which core it's going to run. So here, this is how to implement the software mitigation control, still with interferences, because if you don't apply time partitioning between the two, you will have concurrent access, which will create interference, but that can be acceptable. So that's another option. The other one, which is more an hypervisor-based solution, which is to have a client-server kind of approach. Here again, you will have an interferences if you don't segregate in time the execution of each of these, but that's another approach where you can control the physical access to the hardware into the server guest OS. So which means that you reduce the analysis of interferences to the memory and cache aspect here, because the access to the hardware is only made by one guest or application in there. So this is another model. But something you would see that in part, the difference between the SMP OS and the hypervisor is here on who is in charge of the Multicore certification. So something to keep in mind. So you need to sketch a little bit how you want to approach your Multicore certification to see if it's going to be simple to do. And the less people you involve, like for example with the hypervisor, it's easy to push the responsibility to the system integrator to do that. With the SMP OS, that depends a little bit on who is in charge of the OS, if it's the OS, the system integrator or not. And if you start to push things to the application, you may sketch the responsibility in a different way. So the choice of the OS also impact who is doing what. And to manage properly Multicore certification, you need to think about it. So doing a bottom-up, I would say a summary of the key takeaways. Something that is important is to think in advance. And that's really something key, to be sure that you are not going to miss something. Because if you wait for the last minute or the first integration to define the strategy for the multicore certification, I would say you can be 1 or 2 years late on your project, in particular, if you have to change the hardware or change the OS because you found out that your initial choice doesn't fit in the end the performance that the system would require. And here the choice of the OS and the kind of mitigation you would like to implement is going to be important. So that goes to that thinking in advance. And I think that, Karl, you want to add the same for the hardware and the analysis.
Yes, exactly. So thinking in advance what the potential requirements on, for example, the visibility of partition switches or interrupts, or, for example, the visibility of performance counters or hardware event monitors might be, so that you can go on with your interference channel characterization activities, i.e. also the mitigation verification activities, and that mitigations will always have trade-offs, and that what needs to be taken into account there is the balance of performance with predictability and analyzability, and how your mitigation might impact the complexity of your system. And again, that comes into making decisions good and early, so that doesn't go and bite you when you have to come to actually making a certification argument.
We have a question from Ishara. Which L2 cache management mechanism is more robust? Cache coloring through software versus cache partitioning through hardware? Who would like to pick that up?
Okay, to start, Karl, and I can leave it to you for the detail.
Yes.
So I'm going to use a sentence that I will certainly use several times in the discussion. Devil is in the detail. So in particular, I would say the easiest approach is to avoid sharing the cache. You can find some multi-core hardware on which the L1 and L2 cache are specific to each core, and that simplifies the work. Now, if you have no choice, you have a shared cache, you have to do something about it. So I would say that there would be a third option that usually is not talked about, which is what you call a software, which you control every access by software upfront before going, I would say, into the cache. Because the cache coloring, usually when you go into detail, most of the time to avoid a huge penalty or doing software only, you use some of the design of the cache that can associate some specific slice of memory to a cache line, which means that depending on your particular memory address or the address pattern of your memory, it will always go to the same cache line. So the point is to slice your application into only this slice of memory that will always go to the first and second line of cache, and for the second core, the third and fourth, and something like that. Problem is that you are going to, so first the benefit is the fact that indeed you will remove some interferences between the cores, but then as Karl mentioned, you will reduce the size of the cache available for your application. But there's another side effect, is as soon as you use slice of memory to allocate to an application or a virtual machine, if you use an hypervisor, usually the MMU configuration will have some side effect because of the translation buffers. So you may introduce some latencies, but you may win from a deterministic point of view. So exactly as Karl mentioned, it's a trade-off.
Yeah, I don't really have anything to add other than, yes, you can definitely also get very much into the optimization of exactly how your specific architecture matches your specific software. The trade-offs, again, analyzability and complexity. The more you do that, the more complex your system gets, and the more you might be finding it very difficult not just to develop the software for it, but also to analyze it later. So it really depends.
Yeah, and I forgot to add about, you asked cache partitioning. Cache partitioning is usually an hardware things. So you would expect that because it's hardware controlled, the level of performance would be better. But you need to have cache partitioning available. Not all multi-core has it out of the box.
Yep. So an early consideration, again, if it's something that you think you'll require.
Thank you. Had a question from John regarding use of validation, verification for helicopters and how that's performed through Multicore.
So you would still be under the same banner as all aerospace. DO-178C, AC 2193, all these considerations would apply.
Okay. A question from Gilles. It seems focus is mainly on resource contention and therefore performance. Is there any other possible interference identified with Multicore?
Yeah, I'll go, I guess. Yes, so one of the interference channels, for example, that I mentioned was cache coherency interference channels associated, for example, with Snoop requests. So Snoop requests are a phenomenon where, to ensure that the data that might be existing in shared caches, but these might be private caches for a given core that may contain the same data, that data is labeled with coherency labels or coherency bits. Now, to ensure if it's changed on one of these local caches, that that change is reflected in other caches so that they aren't working on stale data and you don't run into conditions where you overwrite data by accident, you have these snoops, which basically broadcast the addresses of changed data to the other cores. So these snoops are processed first to ensure that all the data that is being used is always coherent and is always up to date, which means that an interference channel, for example, is that these snoops have to be handled and that they may block local accesses to a cache. So that's not necessarily a resource contention interference channel, but rather a coherency protocol interference channel, where it comes from multiple cores actually having private caches. So that's something else to be considered. And there are lots of other examples, but I think probably not within the time scale we have.
Yeah, maybe just a quick word, because the people may think about virtual cores, like, for example, some cores can do multi-threading on one core. This is excluded from now from the NC 20-193. It doesn't mean that you cannot do it. It's just that the authority expects you to explain how you really identify the interferences and how you deal with it. So something to keep in mind, that indeed there are other things, but again, even the authority try to make it simple. It's already complex when you have physical cores, so don't deal with virtual cores yet.
Yes, also that is effectively not a multi-core problem as such, because you could do that in a single core as well. Don't.